The outer reaches of our solar system are home to two enigmatic giants, Uranus and Neptune. Unlike the blazing infernos of the inner rocky planets and the massive gas giants like Jupiter and Saturn, these icy behemoths remain some of the least understood worlds in our cosmic neighborhood. Although they are our closest examples of ice giants, their interiors, atmospheres, and magnetic fields present mysteries that challenge long-held theories of planet formation and structure. However, recent advances in computer simulations are beginning to unlock their secrets, paving the way for new explorations and insights. The nature of icy giants. Although similar in size and composition, Uranus and Neptune are strikingly different from the gas giants Jupiter and Saturn. They are often called ice giants because of their high concentrations of volatile substances such as water, methane, and ammonia. These compounds, often in solid or liquid form under extreme pressure, dominate their interiors. Unlike Jupiter and Saturn, which are composed mainly of hydrogen and helium, Uranus and Neptune have relatively small hydrogen envelopes overlying dense, icy interiors. Their location in the cold outer regions of the solar system allowed them to accumulate large amounts of water and other heavy elements during their formation, distinguishing them from their larger counterparts. Despite their abundance of these volatiles, our understanding of their internal structure is limited. Data collected by NASA's Voyager 2 spacecraft during its brief flybys in the 1980s provided some insights, but the information raised as many questions as it answered. Voyager 2's puzzling discoveries. When Voyager 2 passed by Uranus in 1986 and Neptune in 1989, it revealed unexpected features of their magnetic fields. Unlike Earth's strong, stable, dipolar magnetic field, generated by a convective region in the planet's metallic core, Uranus and Neptune have weaker, more chaotic magnetic fields. These fields appear to lack a clear dipole structure and are strongly tilted relative to the planet's rotational axis. This was surprising because planetary magnetic fields are usually thought to be formed by the movement of conductive materials, such as liquid iron or metallic hydrogen, in the interior of a planet. For the Earth, this movement occurs in a convective region where hot material rises, cools, and sinks in a continuous cycle, producing a strong and stable magnetic field. It was expected that Uranus and Neptune, which are thought to have Earth-sized rocky cores surrounded by layers of water, methane, and ammonia, would have similar convection zones driving their magnetic fields. But Voyager 2's findings suggested otherwise. The mystery of convection zones. The lack of a strong, stable magnetic field on Uranus and Neptune raised questions about their internal dynamics. One hypothesis was that the layers within these planets might not mix well, preventing the formation of a convection zone. This would mean that instead of a dynamic churning of materials, the interiors of these planets could be stratified, with distinct layers that remain separate, like oil and water. Such stratification would fundamentally change the way heat and material move within the planet, disrupting the processes that generate a strong dipolar magnetic field. However, testing this hypothesis proved to be a formidable challenge. The extreme pressures and temperatures inside Uranus and Neptune are impossible to reproduce in the laboratory, and without new spacecraft data, researchers have had to rely on theoretical models. Improving understanding through simulation. In recent years, advances in computational science have enabled researchers to simulate the behavior of materials in the extreme conditions found inside giant ice caps. In a recent landmark study, computer simulations were used to model the interactions of more than 500 molecules, providing new insights into the bulk properties of water, methane, and ammonia at high pressure and temperature. The simulations showed that in the middle layers of Uranus and Neptune, these volatile compounds separate into two distinct, immiscible layers. This separation is mainly driven by the expulsion of hydrogen from the deep interior, which disrupts the potential for mixing. Without the turbulence and movement of material that a convection zone provides, these layers remain stable and stratified, explaining the chaotic and weak magnetic fields observed by Voyager 2. This finding is consistent with the idea that Uranus and Neptune are fundamentally different from the gas giants. Uranus is thought to have a rocky core about the size of Mercury, while Neptune's core is closer to the size of Mars. Above these cores lies a vast, dense layer of water, ammonia, and methane, covered by a relatively thin atmosphere of hydrogen and helium. Implications for planetary science. The implications of these discoveries extend far beyond Uranus and Neptune. Ice giants are among the most common types of planets discovered in other star systems, making them crucial to our understanding of planetary formation and evolution. The newly discovered stratification model could help explain why exoplanets with similar compositions have different magnetic and atmospheric properties. Understanding the interiors of Uranus and Neptune could also shed light on the early solar system. These planets probably formed in a region rich in ice and volatiles, trapping materials that were abundant in the protoplanetary disk. By studying them, scientists can piece together the conditions and processes that shaped our cosmic neighborhood billions of years ago. Future missions and experiments. Despite this progress, much remains unknown. Future laboratory experiments could confirm the simulated bulk properties of water, methane, and ammonia under extreme conditions. High-pressure facilities and advanced materials science techniques could replicate some aspects of the interiors of ice giants, providing experimental validation of computational models. But the real breakthrough will come from direct exploration. NASA is considering a dedicated mission to Uranus that could launch within the next decade. Such a mission would include an orbiter and possibly an atmospheric probe capable of gathering detailed data on the planet's composition, temperature, magnetic field, and atmospheric dynamics. Similar missions to Neptune could follow, providing a comprehensive picture of the icy giants. The bigger picture, ice giants as cosmic laboratories, Uranus and Neptune, are not only fascinating worlds in their own right, they are windows into the wider universe. As we discover more exoplanets that fall into the category of ice giants, these distant neighbors in our own solar system will become natural laboratories for understanding their counterparts across the galaxy. By unlocking the secrets of their interiors, atmospheres, and magnetic fields, we will gain a deeper appreciation of planetary diversity and the forces that shape worlds. Long overshadowed by their more famous planetary siblings, Uranus and Neptune are finally stepping into the spotlight as keys to some of the universe's deepest mysteries,